you have done with these models? Shall we proceed? So now we have these two potentials, open circuit and concentration. Not concentration, actually it is activation. So as literature proposes that we can easily neglect the concentration losses when we are operating below 3 ampere per centimeter square. So here we doesn't account the concentration losses for this case. First of all, we calculated here we open circuit.
Which one you change from concentration to activation? They are asking that. The
yes,
second.
This is activation only. Yes, ma'am. Open circuit voltage and activation voltage. So we have first go to block here. So from this go to block we can directly by swapping or just by typing manually from, we can get this from block here. Like just type from and they ask for, it asks for go to tag, or just we have to write which you have defined for that UOC cell, or it is created. Am I clear? Next we have to do similar for activation potential, or we can do one thing, just by swapping it we can get the activation potential from block for that. So now we have to find the summation for these two potentials. So we can counting the cell voltage equation, which says that V cell is equal to V ohmic plus V activation plus V open circuit or reversible plus V concentration. We are trying to implement that only. Ohmic losses are accounting in the circuit itself, so we have to find only activation and open circuit voltage. So now we write sum, we get this sum block. Just write U cell or V cell, whatever you want. Number of cells in series. So we have created this from block from this go to and multiplied by number of cells to get the actual voltage. So now search for product. And now create one more go to block. And name it as VTH, threshold voltage.
All of you reach to this point?
Done.
Okay. Students?
Towards circuit construction. First of all, we have to search controlled voltage source. And just give the control signal to controlled voltage source. I hope it is visible.
Please carefully write the variable names. It is R underscore ohmic underscore PEM.
Measurement block. Measurement block with resistance like shown in like shown on the screen. Please connect the voltmeter with the resistance. Now create one go to and one display, and name it as I. Like in activation potential calculation, we define that variable I. So from this circuit, we are calculating that value.
So backside, sir. Are you getting it? Okay. You? Oh, okay. So this is basically a dynamic equivalent model of electrolyzer. But while modeling the potentials, we also included the electrochemical reactions. Of course, we are not putting the chemical equations directly, but we are designing or in terms of a over potential that is calculated from the measured current, measured input current, you can say. And all the PDF you are given, all these expressions are shown there. And this is a simple electrical model. As you will complete today, so what we will do tomorrow, if you see, we are connected this to a constant DC voltage. Now in reality, that DC voltage will not be a constant. It will be the output of a DC-DC converter. So that DC-DC converter along with the controller with this load tomorrow will show. So let's complete this today totally so that you can use this model tomorrow. I want everyone to type it better. It's like not that much long, just the equations you understand how to type. Okay, can you start from beginning? Will be saved. After you successfully run this, then you run your model and see it is properly running or not. Check once. If it not recognizing some variable,
Our interface that we have neglected in the equations.
actually. So connect that, copy that and connect inside itself for time being.
It is by default value.
No, we'll see now how much is.
Just do one thing, import one DC voltage source.
How much voltage you are giving.
This
So
is
here depends, you are designing a cell or you are designing a stack. So if you are designing a cell, then you have to give a cell level input. If you are designing a stack, you have to give stack level input. So for firstly, what you want to see? So
we have to design for cell.
basic
one.
So cell voltage is basically
3 volt.
3 volt we gave.
Here. It
So if you remember the equation, V cell is equal to sum of all potential, right? So V cell is the input DC is equal to B ohmic plus all other over potentials. So all over potentials we model it as a control voltage source plus B ohmic equal to V cell. Understood? So if you see it is a control voltage source. So that control signal is the summation. Can you show which one? U cell, right? That is the summation of two potential, and after this two potential you are left with ohmic. So this two potential plus ohmic is equal to V cell. Get it?
transfer function block. Like in our electrical model, we have a capacitance. So here to represent that tau, time constant RC, we are having this value because our electrolyzer has some capacitance effect in inbuilt double layer capacitance. Due to that inbuilt double layer capacitance, that's why we have this transfer function block here. We can replace it by unit delay function, or in simulation, if we want to ignore that, we can ignore. But ultimately, it can causes the algebraic loop error in our simulation. So for that's why we have to consider it also.
Of an actual electrolyzer cell. So that is, you can see what is the double layer capacitance, and that effect we model it in terms of a first order transfer function to give some dynamics. Okay.